Mathematical models can be used to approximate a distribution of data. The most common mathematical model is the normal distribution. In this video, I want to show you a real data set and then use the normal distribution as a model for these data. Here is a document that shows the SAT score for everyone who took the SAT in 2014. The scores in this document are the combined critical reading, mathematics, and writing scores. The table is a frequency distribution. In the first column are the possible scores. In the second column are the frequencies for each score. That is, we can see how many students obtained each score. For example, 630 of the students who took the SAT in 2014 obtained a score of 2350. The third column shows the percentile rank for each score. For example, an SAT score of 2100 has a percentile rank of 96. Another way to say it is that the 96th percentile of the SAT is a score of 2100. There are other scores that are also the 96th percentile. This happens when you have many test takers. The percentile rank tells us the percentage of students that scored below that percentile. So 96% of those who took the SAT in 2014 scored below 2100. Percentiles are integers, but if we were to calculate the percentage of students who scored below 2100, the result would not be an integer. Rounding to the nearest integer gives us 96. Yet the same thing happens when we calculate the percentage of students who scored below 2090 and then round to the nearest integer. We're also going to get 96. Whenever we look at percentile ranks with many test takers, we're going to see the same rank appear for multiple possible scores. Conversely, if you calculate percentile ranks when you have a small number of test takers, there will be some percentile ranks that never occur for your data. Percentiles and percentile ranks are based on frequencies, so they are dependent on the size of the data set. The table also gives us separate information for males and females, but let's focus our attention on the total number of students without disaggregating by gender. If I want to know the total sample size, I can add up all the frequencies for every score. I don't want to do this by hand because I have a nice calculator. That calculator is called R. I have already put the scores and frequencies from this table into an Excel file, saved the Excel file as a CSV file, loaded that into R, and saved the object with these data into an R data file. Now I can load that into R, and I'm going to do that right now. The table provided 181 unique SAT scores, so I have 181 observations or cases or rows if you want to think of this as a spreadsheet. There are 4 variables. I'm only going to focus on 2 of these, the score and the total frequency. The other 2 are the frequencies for each gender. Now what I really want is to have a student as the unit of analysis. I need to expand this object so that there are as many rows as there are students, and so that I have a score for each student. For example, right now, the top score of 2400 only appears once in my object, but I want 583 rows with the score 2400. For the score of 2390, I want 237 rows with that score, and so on. Can R do this? Oh yes. And I'll tell you that many other statistical software packages cannot do this. The beauty of R is that it is constantly being expanded by statisticians and by people like you and me who need new functions. Sometime in the past, someone needed to do exactly what we need right now. They created a repeat function. They used the abbreviation rep. I'm not going to spend time explaining this function right now because you don't need to thoroughly understand it at this point in your statistical life. Just note that we are going to repeat rows for each score of the SAT based upon the frequency of students who earn that score. I'm going to put that result into a variable that I'll call SAT.expanded. In the environment window, we can see that this new variable contains 1,672,395 elements. That's how many students there were who took the SAT in 2014. This is a quantitative variable, and I'm most interested in the shape of the distribution of the data, so I want to create a histogram. Here's my histogram statement. The first parameter is the variable name. The breaks parameter tells the function how many bars I want. I had some trial and error behind the scenes to determine that 180 will work well. The xlim parameter provides the range of the horizontal axis. I went below and above the actual SAT scores just a little bit so that my histogram will show all the scores with a little extra on both the left and right side of the horizontal axis. I then labeled my axes and gave this histogram a title. I'm going to expand the window where my plot is going to appear so that the plot will be a reasonable size for viewing, and then I'll run the function. Here's the histogram. Does that look like a normal distribution or what? I'm not surprised by this because the SAT is purposefully created to result in a normal distribution. What we are looking at is the actual distribution of the data. A normal distribution is a mathematical model, so let's superimpose that model on this distribution. I'm first going to create an x variable using the same range of scores that I did when creating the histogram. I'm creating these scores in increments of 10, just like SAT scores. The vertical dimension needs to be the density of the normal distribution, so I'm using the normal distribution function dnorm. I provide that function my score, but I also need to tell it which normal distribution to use. There are an infinite number of normal distributions. Each is defined by the mean and standard deviation. Let's look back at our original table. If we scroll all the way to the bottom, we see that the mean for these data is 1497 and the standard deviation is 322. Let's use these as our parameters. If I go directly to the plot command, it will erase my histogram. I don't want to do that. There are various ways to avoid erasing the histogram, but one of the easiest is to use the par function. Par is short for parameter. This function allows us to set various parameters for our graph. Setting the new parameter to true tells R that we want a new plot on the same graph. That's not obvious or intuitive to any of us, but I looked it up and that's what it does. That's what I do whenever I use R. I search for functions that will do what I want to do, use them, then promptly forget, so I must look it up again the next time. Unless it becomes a function that I use repeatedly, then I might finally remember. Let's plot our horizontal and vertical variables as a line graph using a red curve within our specified range. I tell the plot not to draw any axes or label either of the axes because I've already done that with my histogram. Let's run it. Not bad, hey? It's not perfect. One reason is that models are meant to represent the general form of a distribution of data. They are never perfect. Also, the SAT is designed to be a normal distribution with a certain mean and standard deviation. Over time, due to changes in students, changes in instruction, changes in educational policies, changes in economics, and so on, the distribution of scores start to drift from what they were when the SAT was first constructed. The SAT was designed to be a normal distribution with a mean of 1,500 and a standard deviation of 300. Notice that in 2014 the mean was 1,497 and the standard deviation was 322. Every few years the College Board, which creates and administers the SAT, will redesign and recalibrate the test. Then, once again, as the years go by, the actual distribution of scores will drift from the original calibration. Using a mathematical model is one way that we can detect this drift. In the next video, I'll show you some other uses for this mathematical model as it is used to model SAT scores.